Hi everyone, welcome back to this video series on Bitcoin. Seeds and Mnemonic codes BIP39. HD wallets are a very powerful mechanism for managing many keys and addresses. They are even more useful if they are combined with a standardized way of creating seeds from a sequence of English words that are easy to transcribe, export and import across wallets. This is known as a mnemonic, and the standard is defined by BIP39. Today, most Bitcoin wallets, as well as wallets for other cryptocurrencies, use this standard and can import and export seeds for backup and recovery using interoperable mnemonics. Wallet best practices. As Bitcoin wallet technology has matured, certain common industry standards have emerged that make Bitcoin wallets broadly interoperable, easy to use, secure and flexible. These most common standards are Mnemonic code words based on BIP39, HD wallets based on BIP32, multi-purpose HD wallet structure based on BIP43, multi-currency and multi-account wallets based on BIP44. These standards may change or may become obsolete by future developments, but for now they form a set of interlocking technologies that have become the de facto wallet standard for Bitcoin. The standards have even been adopted by a broad range of software and hardware Bitcoin wallets, making all these wallets interoperable. A user can export a mnemonic generated as one of these wallets and import it in another wallet, recovering all transaction keys and addresses. Some example of software wallets supporting these standards include listed alphabetically Bread Wallet, Copay, Multibit HD and Mycelium. Examples of hardware wallets supporting these standards include listed alphabetically Keep, Key, Ledger and Trezor. The following sections examine each of these technologies in detail. Using a Bitcoin wallet. In Bitcoin uses, users and their stories. On page 5 we introduce Gabrielle, an enterprising young teenager in Rio de Janeiro who is running a simple web store that sells Bitcoin branded t-shirts, coffee mugs and stickers. Gabriel uses a Trezor Bitcoin hardware wallet figure 54 to securely manage his Bitcoin. The Trezor is a simple USB device with two buttons that stores keys in the form of a HD wallet and signs transactions. Trezor wallets implement all the industry standards discussed in this chapter, so Gabrielle is not so reliant on any proprietary technology or single vendor solution. When Gabrielle used the Trezor for the first time, the device generated a mnemonic and seed from a built-in hardware random number generator. During the initialization phase, the wallet displayed a number sequence of words one by one on the screen. See figure 5.5. By writing down these mnemonic, Gabrielle created a backup C table 5.1 that can be used for recovery in the case of loss or damage of the Trezor device. The mnemonic can be used for recovery in a new Trezor or in any one of many compatible software or hardware wallets. Note that the sequence of words is important, so mnemonic paper backups have numbered spaces for each word. Gabrielle had to carefully record each word in a numbered space to preserve the correct sequence. So here's Gabrielle's paper backup of the mnemonic. For the first implementation of his web store, Gabrielle uses a single Bitcoin address generated on his Trezor device. This single address is used by all customers for all orders As we will see, this approach has some drawbacks and can be improved upon with a HD wallet. Mnemonic code words BIP 39. Mnemonic code words are word sequences that represent in code a random number used as a seed to derive a deterministic wallet. The sequence of words is sufficient to recreate and seed, and from there recreate the wallet and all the derived keys. A wallet application that implements deterministic wallets with mnemonic words would show the user a sequence of 12 to 24 words when creating a wallet. That sequence of words is the wallet backup and can be used to recover and recreate all the keys in the same or any compatible wallet application. Mnemonic words make it easier for users to back up wallets because they are easy to read and correctly transcribe as compared to as a random sequence of numbers. Mnemonic codes are defined in BIP 39. Note that BIP 39 is one implementation of a mnemonic code standard. There is a different standard with a different set of words used by the Electrum wallet and predating BIP 39. BIP 39 was proposed by the company behind the Trezor hardware wallet and is compatible with Electrum's implementation. However, BIP 39 has now achieved broad industry support across dozens of interoperable implementations and should be considered the de facto industry standard. Generating mnemonic words. Mnemonic words are generated automatically by the wallet using the standardized process behind BIP 39. The wallet starts from a source of entropy, adds a checksum, and then maps the entropy to a word list. Create a random sequence entropy of 128 to 256 bits. Create a checksum of the random sequence by taking the first entropy length 32 bits of its SHA256 hash. Add the checksum to the end of the random sequence. Divide the sequence into sections of 11 bits. Map each 11-bit value to a word from the predefined dictionary of 2048 words. The mnemonic code is the sequence of words. So here we see in figure 5.6 shows how entropy is used to generate mnemonic words. So I'll just leave that on the screen there for a minute so you can take a look at it. So you can see here generate entropy 128 bits, SHA256, first 4 bits, entropy 128 bits, checksum 4 bits, 4, split 128 bits into 12 segments of 11 bits each, 5 BIP English word list 2048 words, and so on. Entropy bits, checksum, entropy, checksum, mnemonic words 1284132 12 160 5165 15 192 6198 18 224 7231 21 256 8264 24. From the mnemonic seed, the mnemonic words represent entropy with a length of 128 to 256 bits. The entropy is then used to derive a longer 512-bit seed through the use of the key stretching function PVKDF2. The seed produced is then used to build a deterministic wallet and derive its keys. The key stretching function takes two parameters, the mnemonic and assault. The purpose of assault in a key stretching function is to make it difficult to build a lookup table enabling a brute force attack. In the BIP 39 standard, the assault has another purpose. It allows the introduction of a passphrase that serves as an additional security factor protecting the seed. The process described in steps 7 through 9 continue the process described previously in generating mnemonic words. The first parameter of the PBKDF2 key stretching function is the mnemonic produced from step 6. The second parameter to the PBKDF2 key stretching function is a salt. The salt is composed of the string constant mnemonic concatenated with an optional user supplied passphrase string. PBKDF2 stretches from the mnemonic and salt parameters using the 2048 rounds of hashing with the HMACSHA512 algorithm, producing a 512-bit value as its final output. The 512-bit value is the seed. So you can see here figure 5.8 shows how mnemonic is used to generate a seed. Mnemonic words: army, van, defense, carry, jealous, true, garbage, claim, echo, media, crunch, sort, mnemonic, optional passphrase, key stretching function, PBKDF2 using HMACSHA512, 2048 rounds, and I'm not going to read all this because it's too long. Table 5.3, 128-bit entropy mnemonic code, no passphrase, resulting seed entropy output 128 bits, 0 C1E24E591 9D297E14 D45F14E1A1A. Mnemonic 12 words: army, van, defense, carry, jealous, true, garbage, claim, echo, media, crunch, passphrase, none. C 512 bits. So we move on here to the next one. Table 5.4, 128-bit entry mnemonic code passphrase resulting seed entropy 128 bits, 0 C1E24E591 9D297E14D54F14E1A1A. Mnemonic words: army, van, defense, carry, jealous, true, garbage, claim, echo, media, crunch, passphrase. So they're pretty much the same. So we'll just move on another little bit here. Optional phrase in BIP 39. The BIP 39 standard allows the use of an optional passphrase in the derivation of the seed. If no passphrase is used, the mnemonic is stretched with a salt consisting of the constant string mnemonic producing a specific 512-bit seed from any given mnemonic. If a passphrase is used, the stretching function produces a different seed from that same mnemonic. In fact, given a single mnemonic, every possible passphrase leads to a different seed. Essentially, there is no wrong passphrase. All passphrases are valid and they all lead to different seeds, forming a vast set of possible utilization wallets. The set of possible wallets is so large, 2512, that there is no practical possibility of brute forcing or accidentally guessing that is in use. The optional passphrase creates two important features. A second factor, something memorized that makes a mnemonic useless on its own, protecting mnemonic backups from compromise by a thief. A form of plausible deniability are duress wallet, where a chosen passphrase leads to a wallet with a small amount of funds used to distract an attacker from the real wallet that contains the majority of funds. However, it is important to note that the use of passphrase also introduces the risk of loss. If the wallet owner is incapacitated or dead, no one else knows the passphrase. The seed is useless and all the funds stored in the wallet are lost forever. Conversely, if the owner backs up the passphrase in the same place as the seed, it defeats the purpose of a second factor. While passphrases are very useful, they should only be used in combination with a carefully planned process for backup and recovery, considering the possibility of surviving the owner and allowing his or her family to recover the cryptocurrency estate. Working with Mnemonic codes, BIP39 is implemented as a library in many different programming languages. Python Mononic, the reference implementation of the standard by Satoshi Labs team that proposed BIP39 in Python. Mnemonic BIP39 an implementation of B39 as part of the popular Bitcoin JS framework in JavaScript. Libitcoin Mnemonic, an implementation of BIP39 as part of the popular Libitcoin framework in C++. There is also a BIP39 generator implemented in a standalone web page, which is extremely useful for testing and experimentation. Figure 5a shows a standalone web page that generates mnemonic seeds and extended private keys. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing, and give me a thumbs up. Thank you.